Zoom recording.
Yeah, all that recorded.
It's fine. That's the introduction. The important part is gonna come now. All right. Thank you, Ray. Hello, Daniel. Okay, so we are just before we're in task one, we're preparing for connection. So before actually getting to the code, I wanted you to give them an introduction into the Lidar itself. I was waiting for you to go into the technical aspect of it. So let me just pull out the technical sheet. All right. So please explain them how the Lidar works and why are you the best at it.
So, okay, thanks. The way the Lidar works is it's basically called it's a time of flight sensor. This means it measures the time it takes for a beam of light to hit an object and then be reflected back. The way the Lidar does this is it has a laser that's spinning inside of the Lidar. And as that laser spins, it pulses an infrared light. And as it pulses that light, it measures how long it takes for a reflection of that beam of light that it just pulsed to return to the sensor. Now, once it knows that time, it can take that and it can figure out how far away objects are from it. If you guys, this LiDAR can do up to 10 meters. It's rated for up to 10 meters range, and then it'll do technically up to 25 meters, but its accuracy will drop. Yeah. Anything else about that, Jorge?
Well, I was about to show the client and server, so we can go a little bit deeper on that. All right. So, Daniel, can you explain them what the Lidar and server basically will do while I have it set up?
So this code is just an example code for the PySystem library. It will it allows you to send LiDAR data from the scuttle or the LiDAR really all the way to your laptop, and then it'll display that data on a plot, a polar plot. It's just a really easy way to see what the LiDAR sees, and helps you make some like quick stationary maps of your surroundings.
Daniel, what is the PySystem library and why is important on this?
Yeah, so the PySystem library is what allows you to grab data from the LiDAR over USB. The way it returns data is as a NumPy array. It returns data, it can return up to 811 points. It will tell you, it returns 2 pieces of information per data point. That is what angle it read that data point at and the distance of that data point.
Daniel, do you remember what was over here? It was polar, that true, right? What equals true?
Yep. Lowercase p.
This is gonna be much clearer once we get this working. All right, so. All right, Daniel, go ahead. I'm gonna be walking in front of the Lidar. I have a better USB camera.
Yeah, so in this map, you can see the way the LiDAR works is you should think of the LiDAR as a point source of light. So if you just imagine like a light bulb in the center of a room, everywhere the light hits would be the part that it maps, and everywhere that you have your shadows are parts of the room that the LiDAR cannot see from that point in the room. So as Jorge walks around the room, this LiDAR is spinning and it's measuring. You can see Jorge's around the 100-degree mark right now. He's going to the left. And you can't see any of the information behind Jorge. It only sees the first object that it hits. So this LiDAR has 270 degrees of field of view, and it works on a single plane. You can also see out here, there's some data points that are hitting the, so if you look on the y-axis of this polar plot, you can see there are some data points that are yellow, or they're the points at the 10-meter mark. The y-axis units are in meters. So you can see the LiDAR's plotted the room, and then there's some points that just go off and hit 10 meters. Jorge, is there a window or something in the room?
Yes.
So what those points are is, in this code at least, if it sees a point that's further than 10 meters away, it just sets that point at 10 meters. And these points are either points that are getting lost, so it sends out a light of a pulse of light, and that light never returns, or it returned at a very large distance. Then because I don't want this map to auto scale so that the room is really tiny, I just set the max distance to 10 meters.
All right, so I got a question for you, Daniel. So when I'm pointing the LiDAR straight ahead to the window, what's the expected output should be?
So with Windows, you might get some fuzzy results. For example, some amount of the these LiDARs work with infrared light, and some Windows at least are transparent to infrared, and some are opaque. So you might get points that are somewhat hit the window, and then some pass through the window. So you'll get really fuzzy results there. So you won't get solid lines like you do on these walls around you. Yeah,
Okay,
you might,
so
and you get the same thing around mirrors as well.
back to the walls. So the line that we can see right in front of the LiDAR. So before that, Daniel, we know that zero degrees. So looking straight ahead would be, if the LiDAR 0 degrees will be straight ahead, right? So it's basically what's in front of it. It will be the 0 in this plot, right?
Yeah, at least in the L1 LiDAR. In this plot, it's not correct. It's 0 degrees is on the right side, 90 degrees off. But yeah, on the L1 LiDAR, 0 degrees would be directly in front of you, and then it goes to from minus 135 degrees to positive 135 degrees.
All right. So you why can't we see the wall? All right. I just wanted you to explain them why can't we see the wall, and why can't we see the wall on the left? So for example, these points on the green points right here. What's the color coding on your map?
In this case, it is distance.
Distance. Okay. And what happens when I put my hands on top of the LiDAR, like this?
Yeah, so interesting thing you could see is when Jorge will cup his hands around the LiDAR. If you have, you can here see the individual points, because this LiDAR has, if I remember correctly, a 2 centimeter resolution. So any distance value that it'll return has a accuracy of plus or minus 2 centimeters. And here you can see as he cups his hand around the LiDAR, it's measuring the points that are very close to it. And it doesn't return 0, it returns around about 3 centimeters, because if you were to look at the LiDAR, can we go to the manual of the LiDAR?
Yes, sir.
Where it shows the dimensions.
1 second.
That was it.
The one on the bottom. Okay.
Yeah. Oh, it doesn't really say, but that so this black dome part is is around about 3 centimeters radius. So that's the closest that Jorge can put his hands to it. Also, it's an important thing to know that when you're using your LiDAR, the plane that the LiDAR operates in, since it's a 2D LiDAR, is at the marker on the back of the LiDAR. So you can see here, Jorge has highlighted 11. That little marker on the back of the LiDAR tells you that's the plane that LiDAR is operating at.
Okay, I got a, yeah.
How high up is that?
I mean, it depends on where it's mounted on the scuttle. If you mean how high is it up from
Well,
the
yeah,
bottom
I
of
mean,
the
for bring
lidar,
it, right.
it looks like about 2.5 inches. I'm just
Okay.
looking at the actual dimensions of the.
These units
Yeah.
are in inches.
Yeah.
Yeah, here. Yeah. Also, Daniel, let me go back to the questions. Do we have any surfaces that can affect the readings, like let's say a shiny object or a reflected object? Would that affect the reading?
Yeah. So, as you scan around the room, you're going to hit different surfaces. So this lidar works with infrared light, um, just like regular light. Infrared light can be reflected, can be scattered, it can be absorbed. So if you hit an object that's that absorbs infrared light very well, so maybe it's like a black surface, if this was visible light, um, then you might not get any infrared light reflected back, or very small amount of infrared light reflected back, and so you might get a really poor reading for that part of the room where the points are either scattered or completely like at they're they're getting really far distances. There's other surfaces like a mirror. A mirror will actually can reflect away points so that they never return to the lidar. So the lidar might return either a 0 or a distance that's very far away for those surfaces as well. Um, as you use the lidar, you'll notice like things that absorb light very well will give you really poor readings, and things that give you that are like solid walls and stuff, you'll get great readings on. So as you make scans of stuff around you, be aware of where you might be getting funky readings, especially if your scuttle is going to be making decisions off of this data.
Yeah. For example, look, Daniel, I'm shining my iPad or my tablet to the lidar, and you can see it right in front of it how it's losing the points.
Yeah, so you can see your iPad's not 10 meters away.
Yeah.
But here it says it's like the points are lost. It's getting really wild values. So yeah, that's a really good example.
All right. So okay, let's go back to the lab for 1 second. All right. So the first thing that we're gonna do is install the Pi USB libraries on, or let me just stop the server from running. So the first thing we're gonna do is install the Pi USB library, which I think we already did that. Since I already did that, it should be everything satisfied. So we're gonna go into the next one, which is installing the Pi 16 library. And that's basically downloading and installing all the necessary stuff to deal with the lidar. You can see that it says already satisfied. All right, already satisfied as well. So we're gonna go into the next part. So now we need to download the files, the following files from GitHub. And if you wanna follow me and take notes what's going on with the code, we're gonna go to Python and then basics. And then we'll have L1 lidar right here. And we have L2 vector down here. And the level 3 code will be in labs in lab 8 template. All right, so these are the 3 codes that we're gonna be using during the lab today. All right, so now that I already have them right here in the Scuttle software, and then basics, I already have them downloaded and I have them open right here, okay? All right, so we're gonna use the level 2 code on this task to run one kind of a scenario, which is gonna be finding the closest vector to the lidar. Okay, so we're gonna go over the code So we have the L1 lidar right here, and this L1 lidar, it was a code written to basically get the data points from the lidar, so that the measurements on it, and then also an angle, a corresponding angle to each data point was assigned. All this code is very well commented, so you can literally follow it step by step.
There's
It's
some
good. Yeah,
question in the chat just asking if you can make the code bigger. It's hard to see the sign.
I can't see my chat.
Also, the PySigTim library should not take long to install. Like, I don't know if I'm going to be very liberal about it, like 2 minutes max. Kind of also depends on your internet connection, but
So
it's
when
not
you,
a big library.
Okay, so is that good? Perfect. Thank you. Also, so when we request information from the lidar, the raw data that we get is 811 points. That's the maximum amount of points that we can get with a resolution of 0.33 degrees. All right, but for the heck of having less data to collect, this code by default returns 54 points. So that and this is where the conversation turns into why 54 points and not the whole 811 points. So the reason we get 54 points instead of 811 is just because the amount of data is a lot. Also the lidar is scanning at 15 hertz, so that means it goes around full revolution 15 times in 1 second, and then if 15 times multiplied by 800 points, that's a lot of data per second, right? So you want to have less data to process at the time. So that's why when you're trying to develop the code for your specific application, you will need to be mindful of how much data I want to actually use from the lidar. I don't know if you want to mention something else, Daniel, regarding the data points.
No, that about covers it. Just make sure for your application, you're grabbing enough points to accurately represent your the space that you're in, but also not so many points because the more points you're grabbing, obviously the more processing time it takes to process those points and even store those points, and the more memory you use in your scuttle. If you calculate it, if you're gonna do a 15 hertz, if you're gonna scan data at 15 hertz, which is what this lidar does, and you're gonna do 811 points every single time, then in 1 second, that's how many points? Let me just grab a calculator here. So that's 12,000 points per second. And then say we're mapping a room. I've tried mapping the MXT lab before. It takes me around 7 minutes to drive the robot around manually to map that room. So I'll multiply that by 7. And that's about 85,000. Let me, wait, my bad. Let me fix my math there. So in a minute, you have about 730,000 points. If I were to map the entire MXET lab in the time it takes me, that's about 5,100,000 points, which is your scuttle will not deal with well. It'll get very slow, and it'll have a hard time showing that data. And actually, if I tried to show that data on my laptop would have a hard time showing that data because that's a lot of points. Now, if I took it down to something more reasonable, say you left it at the default 54 points per scan, that's 54 times 15, so 810 points per second. In a minute, that's almost 50,000 points. And then in the time it takes me to map the room, so like 7 minutes, so that's 340,000 points, which is a lot more manageable than 5 million points of data.
So as you can see, it's a big difference in data. So that's why you have to be mindful of that, seeing what's your application. And then, for example, I'm gonna follow actually the lab again. So verify that the LiDAR is connected to the USB by putting the command ls. Oops, not there. Ls. Oh, it's so slow. ls USB. So you can see that's the device connected to it. That's the LiDAR device. I don't have anything else connected to my USB. Okay, so we're going to the L1 LiDAR. So we need to run the while loop uncommented. Okay, so this while loop is commented right here, uncommented right here. So we're gonna. All right, Daniel, it's a question for you.
Yeah.
How do you deal with noise in the data? On the code, how do you deal with the noise on the software part, basically?
So if you have noise in your data, and that means, say, for example, if you hit, so you can, if you were to take a scan of a room and you have a mirror in that room, typically what happens is that part of the room, that mirror surface is very noisy. So instead of like a plus or minus 2 centimeter deviation, you'll have something like 5 centimeters or 10 centimeters where just points are kind of everywhere. You can do a couple things. So in your code, you can measure that, as I go through this array, so if I'm passing over a wall, which has basically a straight line, the points are within a certain distance from each other. And so I can assume, okay, this is mostly a straight line, or I can do like a best fit line type of thing from a certain section of the map to another section of the map. Now, when I encounter a noisy part of the room, the best thing you can kind of do is average that part out. But you can have issues where you're not properly mapping that section of the room, and you're basically making up the data in that room by averaging it out. So you want to be careful in what situations you do that, just because since it's not specifically being mapped, it might be that data might not be accurate at all. So once again, depends on your scuttle's decision making. If you're manually making decisions for it, it might not matter as much as if it's autonomously making decisions on where to move around the room. Yeah. Does that answer your question, Jorge? Your mic's muted.
At what level of code are we averaging it? Where are we averaging that? Where are you doing this in the code?
So you'd have to do this yourself in your own code. The L1 LiDAR only returns the data from the LiDAR. That's about it.
Okay. So that's a technique that you will use to filter out your data, basically. All right. So any other questions regarding LiDAR technical stuff? Be mindful of the questions down in the questions that you have to answer right here. So
yeah.
Okay, I'm gonna run L1 LiDAR so you guys can see the output. So we're gonna run the while loop uncommented, and we need to verify that there are 54 data points in this way. It's an array of distance, comma, angle. So the angle will be the angle of that measurement. So if we run pseudo item 3 L1 lidar. So you guys can see here that it's outputting. I wish I could scroll, but I don't know. I can't scroll on my terminal in the Beagle for some reason. So I'm gonna run it on my computer terminal, which is also connected to my Scotto. So I can show you guys better. So I'm gonna stop it. Okay, so if you guys want to count it, go ahead and count it, but that doesn't look like 54 points. All right, so I'm gonna save this file again because I had more data points on it. And then I'm gonna rerun this. So, all right, so this looks much better. That is actually 54 points printed right here. So we're gonna start from negative 35 degrees. So that would be one end of the lidar. In this case, it will be the right side of the lidar. So negative 35. Let me put the camera. All right. So in the middle will be degree 0. So if you see my screen, you can see that at 0 degrees here, the closest object to it is at 1.8 meters, which is very accurate since my wall is around 2 meters away from the lidar. And then you have that at negative 135 degrees, which is all the way down here. You can't quite see very well. Oh, here you have this little wall here. So negative 135, and it would say is saying that the closest object is at 0.7 meters, which is also pretty accurate since my computer is that far. And then you also have plus 35. The wall is around 3 meters away from it. Okay, so one cool thing about this L1 lidar is that you can change how many points you wanna obtain. So there is a function called polar scan here that as default, if you pass nothing to it, it will assign the number of points as 54. But if you wanna say I want 811 points, it will send that 811 as it will assign it as normal points. So basically, it's gonna return you 811 data points. So let's run that, see how that looks. There is so much data that my computer decides to just say dot dot dot. That's one of the issues I had dealing with the lidar when I was doing my code. Yes. Yeah. So since I'm asking for 811 points, I don't know why it does this. Like it wouldn't actually print that many points. Daniel, do you know anything about why would do that?
Yeah, that dot means exactly what you think it means. It's just saying this is a lot of data. If you want to print this out, you'll have to do it a different way. For example, you could use a for loop where you just iterate through every element in this NumPy array to grab that data to print out every single line. It's basically telling you, though, yeah, this is a lot of points of data that maybe it's not a good idea for me to print out to the terminal. There are 811 points there, but that dot 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 saying, hey, you probably don't want to print this out to the terminal. But if you want to do it, you can.
Okay. Yeah, this is basically what we're doing here. Also, Daniel, I got a question for you that they're asking. So we have the returning data, which is lidar data, is one array, and the elements of the array are the points, right?
Yeah, it's a NumPy array, and it's basically using it returns the distance and then the angle at which it recorded that distance.
But I guess the question would be, all these points are within an array, right? And all these points are
Yes.
elements of that big array. And that's why we have this outside bracket here,
Yes.
right? So you can access individual points on that reading. So let's say I want to print the element in the middle, say 400. It will just return that element right here, you see? So you can pick which data you want. And also the while loop is repeating every 5 seconds. And you can change that to 0.1 second. And you will get data running much faster. Oh. Right, so that's L1 Lidar. It's very useful regarding my using the Lidar. So okay, now we're gonna go. Any questions about L1 Lidar? Yeah, so it's a 2D array.
Correct.
Yeah, it's a 2D array. Okay, so we're gonna go into L2 vector. So we verified this. So we're going to the L2 vector, and we have here the L2 vector. So this program manipulates distance vector in the robot coordinate frame, as well as arrays of vectors. Pay attention to the format of arguments, since some functions are not yet optimized to handle NumPy 1/2 vector directories. So basically, there is a bunch of functions in here that are being used as well by this. The most important function in the whole script is get nearest. So basically what it does, it just looks into all the data that the Lidar is getting, and is using L1 Lidar to do that. And then it just determines which distance is the, which point has the minimum distance, and it passes the vector as that distance with its corresponding degree, okay? So if we go to the while loop right here, we have that my vector is equal to the get nearest. So get nearest is returning this vector right here. And that will be the nearest vector to the Lidar, right? And then we're gonna print it, right, like this. We're gonna have a small delay of 0.1 second, which we can change later. So if we save this and we run it, I'm gonna run it actually here in the BeagleBone. I don't have to run this as sudo. Python 3 L2 vector. All right, so it depends on your Lidar, right? So since your Lidar is scanning in 2D, as Daniel was mentioning, the actual, I don't like my camera here. So the actual sensor, if you can see my screen right now, is where that 11 point is. So basically that's gonna be the plane. So, actually, I think you can see the light moving inside. Oh yeah, look. Can you guys see it? Yeah, so that's the actual sensor going around and detecting stuff. So that's basically where the plane, that 2D plane that we're talking about is. So that's gonna be the plane where he's gonna scan everything. So everything at this height is gonna be detected by the Lidar. It's actually a good picture. Nice. Yeah. So, and if you get close to it, you can listen to the motor. I don't think we can do that with a microphone. Anyways, I'm gonna point it down again. All right, so we're gonna run that L2 Lidar, L2 vector. The L2 vector. So you can see that the nearest object's been printed, and it's telling the distance of that nearest object also with its angle. So I'm gonna when I have my pen, I'm gonna go around, and you can see that it's picking up my pen, and the angle is changing according to me moving the pen. And you just get a bigger object. Controller. So you guys can see how the measurement is changing. So one useful application of this will be just to detect when objects get close to your robot. So when something is so close that you have to stop, basically, otherwise you're gonna run into it. So that's one of that's the application we use for the lidar in our scuttle. But also there's other applications. Daniel, can you mention a little bit about the scan algorithms? How would you scan a room using the lidar?
So
you map the room? Yeah, sorry.
Yeah, one of the most popular ways to create maps using lidars is using SLAM, which stands for simultaneous localization and mapping. Basically, this means exactly what it sounds like. It's localization and mapping happening at the same time, and this is important because I want to know what my position is in a room, for example. So that I know where walls, what these LiDAR points that I return back, what their locations are relative to me. And so if I know my robot's position while I move through a room, it makes it very easy for me to map where in the room my robot is and what the surroundings of that part of the room look like. And this looks like an NVIDIA video. What is that?
I think this was like cool pictures here.
Yeah, and here they're using a Velodyne LiDAR. This graphic is just showing it's a 3-dimensional LiDAR.
There's some better pictures here.
Yeah, so in here we can see the purple points are the points that are the LiDAR red. You can see there's like a lot of stray points, and that's where your filtering comes in. And this blue line is the path the robot takes around the room. And so if I know my robot's path around as I travel through the room, it makes it very easy for me to plot points. And you might say, so if I'm in a section part of the room, I know how far away walls are relative to me because that's what my data is telling me, is how far away is a point in the room from my LiDAR. But if, for example, your scuttle rotates, then you need to know that your scuttle has rotated so that it can still plot those points in the correct locations around the room as you drive around that room, which is a somewhat difficult problem. But once you get it working, you can produce some really cool maps.
Yeah, here is an animation of the robot basically going and finding its surroundings. You can see how where he goes, everything becomes more clear.
Yeah, so as this robot drives around the room, it's hitting more points that it otherwise could not see. This is where I was talking about. If you imagine your LiDAR as a point source of light, like a light bulb in the center of a room, everywhere there's shadows are places that you cannot see. And so as you move that light around the room, those areas that were initially in a shadow would now be lit up. And so similar to the LiDAR, those are areas of the room that you would now be able to get data back for.
Yeah. Okay, so that's how you will map a room. Also, there's a question about that. How is mapping done using the LiDAR? What type of algorithm is used for mapping? So make sure you add that in there. Also, since we have already run L2 LiDAR, the L2 vector, and we can prove that that's working correctly. And now the last step will be using Node-RED to plot that data, as we can see in the video up here. So now that you guys have a better understanding of how this works, you can see that basically this is what we're gonna use. So I'm gonna add an activity. I'm gonna add an activity for you guys. Yeah, we are not doing anything besides a report, since I can't check out the code. But I'm gonna add an activity for the lab report at the end. It will make you go through. It will make you go through the code that we just reviewed, and you will have to basically you have to plot the data in Node-RED. Since you don't have Node-RED, I will not give you a bad grade if you do it incorrectly. So the report is due next Friday at the beginning of next Friday's lab. Okay, you have a week to write that up. So I'm gonna add an activity on the lab instructions, in which you will be required to, as we did before, just grab the data, grab the functions from the code that we saw, and then you'll be required to make a script that will plot that data into Node-RED. So the lab reports are individual now. So from now on, all the lab reports, we have two more labs left, so they're gonna be individual as well. Okay, so yeah, so the lab, I'm gonna add some details on that later. Actually, after this meeting is done, I'm gonna go back and add that to the activity. The report is due next week. This activity will be done, will be also be part of the report. So I'm gonna add it down here in this area here, so you guys can just write a little bit of code and still go through the L1 Lidar and L2 vector to see which functions you wanna use to plot something like the video, something like this. So you wouldn't have to do any Node-RED activity. You just have to look through the code to see which function will give you the closest obstacle and also the angle. So I just want you guys to make a little script like we done before on the lab templates. What do you mean by constant data?
So yeah,
go ahead.
Since we don't have the actual letter, so we're just gonna use the data that you're gonna give us to do all this stuff, or it's just gonna be a GUI that doesn't change?
No, so you don't have to do the GUI since you don't have access to Node-RED. I just want you to do the Python code for it. So let's you guys remembered when we did the lab templates, that lab templates, sorry, the L3 codes that we had to basically output data to a temp file or whatever way you want to use to log data. So basically you have to do something very similar to this code here. You have to import the necessary Python scripts that you will need to use. You need to import NumPy, everything, and then you have to make a little while loop that imports, that logs, basically. It will log the distance and it will log the angle at where that nearest point is. Very similar to this right here again.
So we are not running the actual code, we are just writing the script.
Yes, yeah, and then you will submit it as you will do it in the normal lab. You will write just a script, and I would make sure I put details on the lab instructions of what I want. It shouldn't be long or difficult. It's just for you guys to actually look at the functions and get help. and all the code that we've done is on GitHub, so you can use that as a reference. Also, if you don't know where to write this code, you can use just a text file, or you can use Notepad++, or you can use anything that you want to write the code. And this will also be a part of the lab report, so you will need to put it on the lab report as well. You wouldn't need to. We have the template for the code. You don't have the template for the code, you will have to come up with your own template. Basically, just follow the L3 submissions that you've done before. So I'm going to make sure that I put that details on the instructions. All right, guys, let's see what's left. So yeah, so that's the part that you guys are basically gonna be doing. I'm gonna make the node thread flow, and you guys are gonna be doing the Python code to log the files. So I'm basically gonna use your Python code to run the node thread and verify that it works. There is no rubric. There is no rubric for the report. You just have to I guess I will have to be more. I just want you guys to just write that report, basically, like we done before. You just have to write about these questions. Also, be mindful about the last one. How can a Lidar be used in industry? Just think about an application where Lidar could be used in a factory, for example. Yeah. Any other questions you guys have? I think like an hour to ask questions regarding the Lidar. Yeah.
So we just answer the questions, or we like write an actual lab report, like introduction, result, and all that stuff?
Yeah. Well, I put report here, but I don't want you guys to write introduction or anything like that. I just want you guys to write. I guess it's not. I guess just write about these questions, like
answering those questions.
Yeah. So make a little paragraph, like a 2-page essay, 1-page essay, 1.5-page essay. I don't know, talking, but you make sure about you mention all these questions on it. Is that clear?
Yeah.
All right. Yeah. I don't want you guys to answer directly the question. I just want you to write something that that I can read that includes all these questions on it. It's basically like a report about the Lidar, like what you learned about the Lidar, and making sure you answer all these questions. Do you guys have any questions?
Paragraph?
Yeah. I guess I wanna make that more clear. Yeah.
Paragraph, not bulletized.
Yeah, paragraph and not bullet. Yeah. As soon as I finish the lab with you guys, I'm gonna make sure that I make more clear instructions regarding what I want for this. You guys have any questions? Okay, so actually I wanted to talk to you guys and see what you think about the final project. I've been discussing a lot with Daniel and Dr. Song regarding the final project. We have some ideas. Some are more difficult to implement than other ones. Since I still want you guys to have access to the scroll itself, we are thinking about the possibility of having a scroll online most of the time of the day, like basically running at least 15 hours a day. And this scroll will be open in the network for anyone to access and test their code on it. So that's one possibility. So basically you will write code for an actual scroll and test it on the scroll. So we're still making up the final project, adjusting to this situation of the coronavirus. But that's one possibility that you guys will have access to a Scuttle to actually test your code and see the error messages. So basically, you will have access to my Scuttle, and then you will have access to Cloud9 and to its terminal. So, so yeah, that's one possibility, and the other one would be just based all simulation. So you write the code and you will write the code and then we'll validate with the simulation, which is not as exciting as actually writing code for the actual Scuttle. So you have any advice or any recommendations on how, or any thoughts on how the final project for the Scuttle should look like, please let me know.
I have a question.
Yes.
So if we do it with the wireless access to a model, we would just have to choose a project that suits the hardware that's already there.
Yes, exactly. So that's a good point. And actually, we were thinking about having very general hardware, so such as a servo motor or an LED light. Something that mimics like an actuator or a movement, something like this. So like you have access to also the hardware. It's like here, so I will have basically something like the lidar and a servo motor connected to like a gripper or something like that. That you will, it's like basically like three options you will have to choose from hardware, and then you will still have to basically do your own task based on the hardware you have available.
Here's a question
yeah.
about, is LiDAR more accurate than the ultrasonic sensor?
Yeah, go ahead.
So those are kind of two different types of sensors. Ultrasonic uses sound, and also it only returns one data point for the distance in front of it. And a laser, which is like doesn't hit, it has a very narrow field of view. If that makes sense. An ultrasonic sensor has a much wider field of view. So if an object isn't directly in front of it, so say off to the side of it, I have an object that is say 50 centimeters away, and then I'm trying to see if I can measure the wall that is 100 centimeters away. I'm probably going to get either 50 centimeters being recorded from my ultrasonic sensor because it's not looking directly in front of it, or I'm going to be getting a mix of 50 and 100 depending on what pulse it gets back first. Yeah, the ultrasonic sensor also only returns 1 point. So if you want to map a room with an ultrasonic sensor, you'd either have to put a couple ultrasonic sensors around your robot, or you'd have to be spinning around your robot around the room every time you want to take a data point. Ultrasonic sensor is distance-wise, the further away you get from the sensor, the more inaccurate its data becomes, and also the larger its the cone of what influence becomes. And so the more it's going to bounce off of things that you don't want to be measuring or that you don't care to be measuring. And radar is very very precise, but also extremely high frequency, and it operates in a very different part of the electromagnetic spectrum. That'd be cool though.
But is it possible like to create a 360 ultrasonic sensor? Because like with Lidar, we have a reflection issue. Maybe with ultrasonic, we don't have that issue.
Yeah, so ultrasonic sensor would be great for, say, doing like mirrors and stuff, things like those surfaces. But the issue mainly with an ultrasonic sensor is that, so like a laser will only see what is directly in front of it. So like if you took a red laser pointer, that point is only going to hit what is directly in front of it. The laser beam, I mean, I guess it technically does, but for the most part, it doesn't get larger and larger and larger. I think of the ultrasonic sensor as more of a flashlight, in that whatever that light's going to really hit first it's either going to be your measurement or it's going to be influencing your measurement. So for the worse. So yes, you could create an ultrasonic LiDAR. I'm pretty sure that's been done before. It's just by mounting an ultrasonic sensor on a spinning platter with a what's it called? Either way, Yes, it could be done, but it wouldn't be as effective at all as a actual LiDAR.
Daniel, another thing that we were mentioning before you joined is that the LiDAR takes in what kind of data, like actual physical data. It takes the strength of the light and also the time it takes to come back, right?
Yeah, the LiDAR technically returns, or at least you can change it in a setting, which I think is enabled by default, but the PySigTim library will let you grab data from the signal strength. So the LiDAR will return both the distance it measured for a point in front of the LiDAR, and it will return what's called an RSSI value. So how much of that, so I pulsed something and how bright was the reflection. That's basically what that is. So if it's like the reflection was very dim, then you'd have a lower RSSI or a lower signal strength. And if it was a higher reflection, it would show a better signal strength.
So you basically will be also not just detecting how far something is, but also you can see the properties of its output out layer, right? You can also see what type of material maybe.
Yes.
Is that possible?
Can you like show a demonstration or a picture of like how the signal is coming back to the LiDAR?
What do you mean?
Like you said, it's a light, so it's reflect back to the LiDAR, like how the signal is coming back, like how we are receiving the signal actually.
So the LiDAR is a time of flight sensor. So yeah, Jorge, see if you can find a good animation of that. But the best I can explain it is the LiDAR being a time of flight sensor, it means it measures the time of flight. So how long it takes for light to hit something and then come back. Now, okay, I'll let Jorge work at that. But basically what it does is inside of the LiDAR, there's a spinning, actually it's not a spinning laser, it's a mirror that spins, and there's a laser at the bottom that's pointing up at the mirror. As that laser spins, it pulses. And what happens is
like this, look.
at a measurement. Yeah,
What do you think?
that's basically it. And it just measures how long it takes. So it'll pulse that laser and it'll measure how long does it take for me to get a reflection back. So that laser light will exit the LiDAR, hit the wall, bounce back, and then I can detect it when I see that laser light again. And then I can take that measurement and use that to calculate how far away was the object, because the further away an object is, the longer it would take for that light to bounce back. The closer it is, the more quickly I'm going to see that light. Does that answer your question?
Yeah, so the reflected light, does it come back on the same trajectory or it can come from another path as well?
So that's the thing. It depends. It always, the light that it senses is going to come back in the same trajectory. And what that means is the LiDAR mostly works well for scattered surfaces that will scatter light. So for example, if you took a regular laser pointer, I can point that laser at a section of the wall and everyone in the room can see that laser, because that laser isn't reflecting light directly back at the person pointing that laser. It's reflecting that light. The wall reflects that light in all directions in that room. So the light that the light that the LiDAR detects is dimmer than what it pulses out, but it's still bright enough that it can see that reflection.
I guess I've actually never seen a LiDAR put on a plane, but I think that's actually very possible, isn't it?
Yeah, no, that's done. That's done a lot to map like rainforest and stuff.
That's very interesting. Also, if we go back to the PowerPoints, yeah, I forgot to mention this part. All right, so we're gonna go into a little bit of the software, a software guide for Scuttle. We have the example. I don't know if you guys remember that the video of the Scuttle following an orange ball that we have on the TVs at the MXET lab. So we made an example of the software architecture on that specific project. So this is the software overview, and a continuation down here. So, but for just the lidar portion of it, if we let me zoom in a little bit, you guys can see that the color code on this software architecture is yellow for sensors, red for actuators, and blue for code modules, and where the logic is being defined. That's where the L2 comes in, and the green ones are the L ones. Is basically hardware specific. So as an example here, you have this module right here that we start with the sensor, which is the TIM 561 lidar. Then we go into the L1 lidar.py, which is the one that gets the information from the lidar, right? So this information is being sent as an array of distances and angles back to the L2. I mean, in this case, it's obstacle.py, but in our case will be the L2 vector, right? So this L2 vector will get the information coming off from the lidar.py, and it will determine which one is the closest obstacle in front of it, and then it will give that information back to the L3 file. That's the one that's taking care of basically putting everything together and taking decisions based on what this module is sending it. Also, you have, let's say, the Gamepad right here. The Gamepad is this module right here. I wanna try to go to the MXET lab and get one of the Gamepads from there, so I can show you guys what this looks like. Basically, you have the sensor as the Gamepad controller, and then you have the L1 Gamepad.py, which I will try to go uncover this next class. There is so many like L1.py libraries that it will be very hard for me to cover all of them. So if you go through all of them and have questions about what they do, it will be awesome. The reason why is because some of this code you can still use it for a Raspberry Pi, and you can build your own robot or your own project based on this code. So if you have the chance to go through the code and look at it and see if you have questions regarding it, this is the best time to ask, since Daniel and I are with you and helping you out. Yes, so we're gonna be learning about computer vision next class. We're gonna do the object detection, object tracking. I'll try to have something prepared for you guys regarding that lab. We're not gonna go in details on it, but I think it's a very important topic. I will want the professor to catch up on the lab since he's still a little bit behind us in the lab. As well, we haven't done the PID controller, the PID part on the schedule, since he's still covering that portion of the class. So once he gets that done, he will go over to the computer vision. So he will actually explain the math and the actual technical aspect of computer vision, and then we'll do a lab to back up whatever you guys learned on the class regarding computer vision. But yeah, this is an example right here. I think, yeah, here, for example, this module right here is the one that is taking care of the computer vision. So you have the sensor, which is a USB camera connected to the BeagleBone, and you have an L1 camera.py. And let me see if we go to that L1 camera.py. You're gonna see that is importing CV2, which is the image processing library that we use for video processing and image processing. Some of you guys are familiar with it, and it sets the desired amount of pixels that you want. It sets up which camera you want to use. Which one is connected to your computer, and there is a function here that takes care of it. Of the image part. So that's an example that we're gonna try to cover next week. So again, you have L1 camera trying to get the images, and then he's also telling the X, Y, and the radius of the object, like where it is on the frame. And this L2 target pi will take that information and will drive the robot to where that object is on the camera frame. So that's just an example. And you can see there is different modules here that make up the robot that you guys saw in the TV. I put on the resources for this lab many slides, so please go over them. There were slides that were gonna help you specifically to do your final project. Here's an example of how your software should look like, the architecture of the software. It's just ways to help you, to guide you to do the final project. I'll try to, when we develop the final project guidelines, to try to see how we can include all this stuff on it, so you guys can have a good understanding of what the software architecture is for and why it's important. So I will try to include that on the final project as well. Let me see which other slides are important here. All the Lidar slides. So we went through the first slide. You guys can see a better picture here of where the Lidar is located on the scroll, its maximum range, and how a wall will be detected. This is the profile of the points, for example. We have a Lidar measuring a point. So P1 is the location of the Lidar right here. The points will be initially measured from Lidar and returned as a pair given by, like this, as L1 Lidar will do. So it will just get the distance D, as you can see here. That's the vector going straight to the obstacle of interest. So let me see. So this software for Lidar. The Lidar scans the frequency of the Lidar, the number of points that L1 that pi returns by default, what L2 Lidar does. So you have a summary of what we did today here. This is how you determine the global position of your obstacle. This is something that Dr. Song will cover during class. When I think he will get, before he goes into computer vision, he will go into obstacle detection with the Lidar. He will explain how can you get the global position of an obstacle with reference, using the Lidar and the scroll. There's just more strategy of how to use the obstacle avoidance, some more materials for you guys to read over. And then you can find velocities, and that's something else that we don't want to go over with this lab right now. But yeah, I give you guys tools and to read over and to finish up the report. I will make an announcement when the actual activity for this lab is done. I'm gonna try to update the last portion of the lab, so it's more clear regarding what we want to do for the report. Yeah. Does anyone want to ask a final questions before we finish this? Also, I'm gonna upload the recording to eCampus, this specific lab. I think this one was very good for everybody to follow if you have any more questions.
Yeah, there was a question in the chat regarding the project. Can you answer that question?
Are you going to be a group? Okay. So it's not gonna be individual for sure. We still, since we have two approaches for the final project. One is controlling the scroll using a server that we set up in my apartment. We will have to schedule, individual times for groups to use the scroll. And if we use groups of 2, it will be too many groups, right? So we could keep the initial idea of groups of 4, but that will make that means that the difficulty of the project would be greater since there is 4 people in the group. Um, and also, I will ask you guys to design, maybe to design a piece of CAD, like a piece of hardware, since that was one of the requirements for last semester. We had to design something that's not on the spot. So it depends. If we're doing that approach, we're gonna use groups of 4. If we're doing the other approach, which is just simulation based, it will be group of 2. Okay, so it's either group of 2 or group of 4, which you already have your group of 2 for the whole semester. You know what your partner is, and also one of your partners, your partner should have the bigger, if not you. And then for the group of 4, you already have that already decided. You decided that already like a week or like 3 weeks ago during class. So either way, you're not gonna be by yourself on the final project. But for the labs, yes, it's individual work. Does that answer your question? All right, guys. If you don't have any more questions, I will finish the recording right here. And